We saw previously that even in the simple case of mass spring oscillator with small amount of damping, when we applied the method of regular perturbations to it, we had a solution which was valid for short times. It was not valid for long times, and therefore we need to talk about a method which allows us to extend the solution to arbitrarily long times. And so we mentioned the method of multiple scales, which allows us to do that. And of course, this is a general method. We're going to illustrate it on this very simple problem so we can work through all the mechanics of it, but it can be applied to more general problems, nonlinear problems, and so on. And so let's look at this method of multiple scales. So here we are going to illustrate this method of multiple scales, and remember that we are solving this ordinary differential equation which has been scaled. The dependent and independent variables have been scaled so that there is one small parameter beta. This is the non-dimensional damping rate as we had defined it before, and tau is the time that appears in this equation, and that has been non-dimensionalized by the oscillation time scale. And the initial conditions are that the initial normalized displacement is 1 and the initial velocity is equal to 0. And remember, beta is this small parameter. And so we start by noting that there are multiple physical timescales. There is the oscillation timescale, which we have used to make the problem non-dimensional, and there is a decay timescale, which when beta is small is a long time, and so the decay is slow. All right. And so to incorporate this physics, we introduce multiple timescales, and so we define these timescales as tau 1, which is same as tau, and we can think of this as the fast timescale. And we introduce then a slow time scale, tau 2, which is beta times tau. So remember, beta is a small number, and so if a clock is moving relative to this time tau 2 relative to tau is progressing very slowly because beta is very small. And so we see this by considering an arbitrary function f of tau, which we now write in terms of its dependence on tau 1 and tau 2. And so now we simply do chain rule. If we evaluate df d tau, we can say that df d tau is the derivative of f with respect to tau 1 times the derivative of tau 1 with respect to tau, and likewise the second term, which is the derivative of f with respect to tau 2 and then derivative of tau 2 with respect to tau. So it's applying simple chain rule, and of course d tau 1 d tau is just 1. That's from this definition. And d tau 2 d tau from this definition here is simply beta. And so we therefore have this general rule that any derivative with respect to time is made up of these two derivatives, the fast derivative plus beta times the slow derivative. All right. So that summation is what we're going to use in coming up with expressions that we need to use with the full differential equation. And so now in this method, we say that the dependent variable v of tau is represented in terms of a series expansion. This is an asymptotic series in terms of successive corrections, but each correction is something which depends on multiple time scales. It depends on the fast time and it depends on the slow time. And then this is a correction of order beta, beta is small, times v1. Again, it depends on tau 1 and tau 2 and beta square v2 and so on. And we put tildes on top of these variables just so that we don't confuse these with the expansion that we had previously done when we did not do multiple scales. We had done straightforward regular perturbations. And so given this expansion for v of tau, we can apply the rule for taking derivative of such a function. And so when we evaluate this derivative, then we can see that at each stage, each of these functions, since it depends both on tau 1 and tau 2, when we take its derivative, we're going to get two terms. One from the derivative with respect to the fast time, and then beta times the derivative with respect to the slow time. And likewise, when we differentiate this, again we get these two terms with this beta factor coming in. And likewise for v2, and if we have more terms, we can just carry them forward. And so given this, we can just rewrite this. This term goes right here, and then we have collected terms which are of order beta. So this term simply is presented here, and this term is shown over here. Beta square, there is no term from here, but here beta times beta gives us a beta square. That's this term sitting over here, dv1 d beta d tau 2. This term is simply from here, and likewise at order beta cube we can write the expression and so on. So you can, if you notice this, you can notice the progression in that how this term and that term are related to each other, in that you can see a recurrence taking place. This pattern is very much like this and so on. So if we needed to write nth term, we can in fact write, because we can observe the same pattern, consistent pattern continuing on. All right, so that gives us the first derivative, and of course we have to do the same thing now one more time to obtain the second derivative. And when we took one derivative, each of these terms expanded into two terms, and so that's going to happen with every term that is present here. And we differentiate one more time, and we already have many derivatives, and so each one is going to expand into two terms, so we're going to get a lot of terms. But the rule for them is very straightforward. We simply have to take each one with the fast and slow time derivatives and assemble them, and that's what we're going to do. So let's take a step in that direction. And so the second derivative, this first term is expanding into these two terms. This term is expanding into these two terms. The second term is expanding into those two terms, and this factor beta is sitting outside. And likewise, this beta square is sitting outside, and this term has expanded into those two. This has expanded into those two, and likewise for beta cube, again the same progression. And so take a moment to look at these terms and so on, and you can see that we have simply applied this rule for taking the time derivative when the function depends on the fast and slow time. And so we simply have this composition rule that we have to take derivative with respect to fast time plus beta times the derivative with respect to slow time for every function that we need to differentiate. And so we simply apply that, and then we have this long expression that we saw, and we can then reorder terms according to the power of beta. And so with respect to terms which have no powers of beta, we have simply this copied over here, and then terms of order beta, we have this term going over here and this term going over here. Order beta square, we have nothing coming from here, and from here we have v1 tau 2 tau 1 derivative, and that's one term, one part in here, and a second one is going to come from the next expression here. So this beta square term is coming from there. This v0, this beta times that beta is giving rise to this term, and the second term here was coming from, hold on, so we're looking for term of beta square, so we have beta square from here, and we have a beta square v1 is coming from here, this with beta square, so that's how we get a factor of 2 here. And so once we have obtained this one, then we can see that likewise we had this progression continuing on. That progression will continue on, so we'll have beta cube with this sequencing of term, which is very much like this, except that we shift the index from 0 to 1, and 1 becomes 2 and 2 becomes 3, and we can write it like that. And so at this stage we now have the second derivative in all its glory with all the terms that you may want to write down, and then the step is that we are going to substitute these expansions for the second derivative, first derivative, and the function into the ordinary differential equation and the initial conditions. And like we have done, we have collected terms at various orders in beta. And so we will collect equations and initial conditions at various orders in beta, and that will define the problem at various orders in beta. And so we will need to solve the resulting equations at each order in beta, and in doing so we will get to pick the dependence on the slow time, because slow time is what we have introduced, and the idea is that we will pick that dependence so that we avoid these secular terms. If you remember, it's these secular terms which cause problem in terms of the fact that the previous solution at each order was a force response with a forcing that was resonant, and so because it was resonant forcing, it would cause the response to grow linearly in time, and that response will become unbounded as time increases, and so that perturbation expansion then is no longer well ordered. And so to avoid that, we have introduced the slow time dependence, And so we will now see how we apply this at each order. So we're going to refer to these expressions in assembling the equations and the initial conditions. So we'll turn to